So let's just quickly recap what we talked about last time. So last time we continued our discussion of pumps, and we started talking about notions of pump power and pump efficiency. So we talked about the ways that we can calculate the input power to a pump. That is the pump that's being applied by the shaft to the impeller. And we also talked about how we could compute the output power of the pump. That is the actual power that is being applied to the water itself to raise its hydraulic head. And if we know the pump input power and the pump output power, we can also characterize the pump efficiency. And generally, we will want our pumps to operate as efficiently as possible. So when we are determining our pump operating point, the pump efficiency is going to be another important factor. So expect some problems related to pump efficiency on the next homework and how you can set the operating point to achieve maximum efficiency. All right, are there any questions on the topics that we covered last class? So we've talked about how we can find the operating point of a pump in a given system. We talked about how we can calculate its power input and output and its efficiency. So in general, our approach is as follows. We have some pump curve that is specified by the manufacturer that provides us the relationship between the pump head and the discharge through the pump. So that is fixed by the pump model. This is the information that's provided by the manufacturer. We then have our system head curve, which describes the discharge and head relationship in the system itself. So basically, this is the head requirement that the pump needs to meet at a given discharge. And this head requirement increases as the flow rate increases because of what? Why does the head requirement increase as the discharge through the pipe increases? Due to losses, yes. Mainly frictional losses, but any kind of loss will cause the head requirement that is imposed on the pump to increase. And our general approach has been to find the intersection between these two curves, which we called the operating point. So the question naturally arises, what if we want to change the operating point? So what if this particular operating point doesn't lie at the point of maximum efficiency for our pump? What can we do? And I mentioned a couple different ways that we can change this operating point. What were some of the ways that I mentioned we could change the operating point? I've mentioned it briefly at the end of class. Yes. You can change the pump speed. So the first way that we're going to explore how we can change this operating point is by changing the pump speed. So as it turns out, we're going to be able to basically shift this pump curve up and to the right or down and to the left by changing the pump speed. So changing the pump speed will allow us to shift this pump curve around if we have a variable speed pump. So not all pumps are variable speed, some of them are, and if they are, then we can shift this pump curve around. Does anyone remember the other way that I mentioned we could change this operating point? Yes? Very good. So we can also use combinations of pumps in parallel or in series. We're going to find that when we do that, we can essentially create a new effective pump curve where you essentially either add together the pump curves in the vertical direction to increase the head, or add together the pumps in the horizontal direction to increase the discharge for a given head range. So we're going to talk a little bit about that towards the second half of class today. I'm not going to draw it here because this is already getting kind of messy. But keep in mind that's what we're going to be doing next. So at the very end of class yesterday, I introduced the idea of affinity laws for variable speed pumps. So these affinity laws give us ways that we can calculate the discharge, head, and power input to a pump running at different speeds. So if I have some rotational speed 1 and some rotational speed 2 given by N1 and N2 respectively, the ratio of the discharges at those two different speeds is equal to the ratio of the two speeds directly. The ratio of the heads of the pump operating at the two different speeds is equal to the ratio of the speeds squared. And the ratio of the power input at the two different speeds is equal to the ratio of the speeds cubed. So let's go through a quick example of how we can use these affinity laws to modify our pump curve. So as I mentioned, it's going to shift our pump curve up and up and to the right or down and to the left, and we'll see that in action. So let's say we're going to consider a pump operating at two different speeds. And we're going to use the same pump that we used in the last example. So our pump, let's say it operates at two different speeds. N1 is equal to 2000 RPM. N2 is equal to 2200 RPM. And let's say we want to compute the new pump curve for the, let's say we have the pump curve for the pump running at 2000 RPM, and we want to compute the pump curve for the pump running at 2200 RPM. So from our affinity laws, we know that the ratio of Q2 to Q1 is equal to N2 divided by N1, and the ratio of the heads, H2 to H1, is equal to the square of N2 divided by N1. So let's say we have a set of discharges for our pump operating at 2000 RPM. We want to compute the discharges for the pump operating at 2200 RPM. What we can do is we can essentially just rearrange this first expression here so that Q2 is equal to N2 divided by N1 times Q1. And if we evaluate this ratio, we get that Q2 is equal to 1.1 times Q1. Similarly, for the discharges, for the pump heads, we have that H2 is equal to N2 divided by N1 squared times H1. And if we evaluate this ratio and square it, we get that H2 is equal to 1.21 times H1. So let's apply this to a pump curve that we've looked at previously. I'll just give you a second to finish writing down. So this spreadsheet that I'm going to show you is located under Canvas Pages, Lecture 14. You can follow along if you'd like, but really here I just want you to get the process down. And I'm going to be opening up Pump Speed Tutorial blank. So when you open up that spreadsheet, you will get the following. So the first column here is, so the first two columns represent our original pump curve at 2000 RPM. So we have the discharges at 2000 RPM and the pump heads at 2000 RPM. And this is the same pump curve that we looked at previously. So let's say I have this original pump curve here and I want to calculate the pump curve operating at 2200 RPM. So first, how can I compute the discharges at 2200 RPM from our original pump curve discharges? Right. So from our expression, we have that Q2 is equal to 1.1 times Q1. So all I have to do is I take column A and I multiply it by 1.1. And that gives us our new set of discharges for our augmented pump curve. All right, and note that we also need to compute the pump heads at this new pump speed. So remember that I gave you this expression here for the pump head operating at 2200 RPM. So we can just multiply our existing heads by 1.21. And this gives us the pump head that is obtained at 2200 RPM. So we have here a new pump curve for our pump operating at 2200 RPM. These two lines here on the plot, the blue line is the original pump curve for the 2000 RPM. The orange line here is our system head curve. So this is coming from that previous example that I showed you. Let's go ahead and plot our new pump curve for the pump operating at 2200 RPM. To do that, I right-clicked on the chart and I'm going to choose Select Data. I'm going to add a new series here. For the X values, I'm going to select column C. So those are our new pump discharges. And for the Y values, I'm going to select column D. And I'm going to give this a name HP 2200 RPM. And I'll hit OK. And this gray line here gives us our new pump curve for the pump operating at 2200 RPM. So you can see that it shifted our original pump curve up and to the right. So this is characteristic of what this pump speed scaling is going to do. It's either going to move your pump up and to the right if you increase the speed, or it's going to move your pump curve down and to the left if you decrease your pump speed. Are there any questions on this example?
You said it goes out of the RPM increases?
Yes. Right. Any other questions on this example? Okay, so I'm going to give you a chance to work on your own example. So on Canvas, under quizzes, I have a Canvas quiz titled In-Class Pump Speed Example. So this is going to have you take an existing pump curve. You're going to compute the new pump curve at a new pump speed, and you're going to find the operating point at the new pump speed. So let me quickly just draw out the problem. So you have two reservoirs that are connected by a cast iron pipeline. Give me 1 second here. All right. Okay, so you have two reservoirs that are connected by a cast iron pipeline. You have a pump in that pipeline. You have that the elevation difference between the two reservoirs is 10 meters. So if you take this distance here, this here is 10 meters. We have that the diameter of the pipe is 40 centimeters. The length of the total pipe is 300 meters. You're going to be using the Hazen-Williams equation for the head losses. And for SI units, this is given by 10.7 times the length of the pipe divided by the diameter to the 4.87 power, divided by the Hazen-Williams coefficient to the 1.85 power, all times the discharge through the pipe to the 1.85 power. So you are given a pump curve at one operating speed. You're going to compute the new operating speed of the pump and then find the operating point of this pump under the new pump speed for this system. All right, so I am going to give you about 15 to 20 minutes to work on this problem. So work in small groups and submit your answers. And then we will reconvene in about 15 minutes and I will walk you through how to start this problem if you have any trouble. So let's reconvene in about 15 minutes. Okay, in the interest of time, let's reconvene. So if you haven't gotten the answer yet, I'm going to walk through how we can start this problem. So let's start the problem. Oops, I don't even have my spreadsheet here. Let me download this one. And we're going to open it. Okay, so first thing, for computing the discharge at 2200 RPM, what do we do? So we can just multiply the discharge at 2000 RPM by 2200 divided by 2000. And we pull that down. For the pump head, we take the pump head at 2000 RPM and multiply by 2200 divided by 2000 squared. And if we want to plot this new pump curve, we go to select data. I'm going to create a new series called 2200 RPM. The X values are going to be this Q range here, and the Y values are going to be this H range here in column D. All right, and that's what your pump curve for the pump operating at 2200 RPM should look like. The next thing we have to do is we have to compute the system head curve. So how do we do that? What is the system head curve equal to? So it consists of two different components that are added together. What are those two components? Yes, so in this case, it'll be the elevation difference plus the head loss. In general, it'll be equal to some static head requirement plus the head loss. So in this case, the static head requirement is the elevation difference between the two reservoirs. So we have that the system head, HSys, is equal to HStat plus K times Q to the 1.85. We can substitute in our known values. So the static head requirement is 10 meters. That is the elevation difference between the two reservoirs. To that, we add our expression for the head losses, which will be 10.7 times the length of the pipe, 300 meters, divided by the diameter to the 4.87 power. So that's 0.4 meters to the 4.87 power, divided by the Hazen-Williams coefficient, which is 100 to the 1.85 power, all times the discharge to the 1.85 power. If you evaluate this expression, you get that the system head curve is equal to 10 meters plus 55.52 times the discharge to the 1.85 power. So for our Excel sheet, we can put that formula in to our column E. This is intended to represent the system head. So this is equal to 10 meters plus 55.52 times the discharge to the 1.85 power. Now, which discharge do I use here? Does it matter? No, it does not matter which discharge you use for your system head curve. it does not depend in any way on the particular pump you are using. We just need to specify a range of discharges to use. The system head curve is entirely independent of your pump curve. So I'm just going to use this set of discharges here. So I'm going to multiply by the discharge to the 1.85 power. We get our system head curve here. We can plot that by going to select data. Let's call this system head, the X values. Okay, now here it matters which X values I'm plotting, right? Because I selected column C to compute the system head. So I need to make sure that when I'm plotting it, I also use column C for the X values. Otherwise, you're going to get the wrong system head curve. For the Y values, I use column E. And with that, we should get our system head curve. And at this point, you can determine the operating point either by using goal seek, using the method we described last time, or by eyeballing it. I would say it's perfectly fine in this case to eyeball it. If you use goal seek, you're going to want to use probably a higher order polynomial because a quadratic one is not going to approximate this pump curve very well. But to eyeball it, what I'd recommend doing is going to chart design, add chart element, grid lines, and then I would add the minor and minor vertical grid lines. So minor horizontal and minor vertical grid lines. This will make it a bit easier to eyeball where that operating point is. And I will leave the rest to you. Okay, are there any questions on this example? All right, so you have until Thursday to complete this. Let's move on to our next topic. First of all, are there any questions in general on pump speed and variable speed pumps before we move on? Yes. The system head curve is independent of the pump curve. So it's just a function that depends on the discharge through the pipe. It doesn't matter what set of discharges I give it. It's just a relationship between the head requirement and the discharge, for a given discharge. It doesn't matter what particular pump you're using. When I go to plot the system head curve, I just need to make sure that the discharges I use to create that system head curve represent the X values for that plot. But in general, I could define an entirely new column with a new set of Q values and use that to compute the system head curve. It doesn't matter if it's pump curve 1 or pump curve 2 or just some other set of discharges. Yes.
The goal seek would just set the polynomial to 0.
Yes. Yeah. All right. Any other questions on variable speed pumps? Okay. So there's another way to shift our operating point, and that is to use pumps in combination. And there's two primary ways that we can add pumps in combination. There are pumps in series and pumps in parallel. Let's talk about pumps in combination. We have pumps in series. So to be clear, that means we have flow coming into some pump. That pump, I'll call this P1, that pump discharges into another pump, P2. And then that pump discharges possibly into some other pump, P3, and so on and so on. So this would be pumps in series. You can also have pumps in parallel. So for instance, a pump that splits maybe into 3 different lines, P1, P2, and I'm running out of space here, but P3. And then those parallel lines converge again. So these are kind of the fundamental building blocks that we can use to construct any kind of combination of pumps that we want. There's two primary ways, pumps in series and pumps in parallel. You'll find that if you've taken any kind of class in electrical circuits, the behavior of pumps in series and parallel is going to be very similar to the behavior of circuit elements in series and in parallel. So let's talk about pumps in series first, because it is the simpler case. So let's say we have flow entering some pump one. That pump one discharges into a second pump, pump two. And pump two discharges into an outlet pipe. So let's say that the flow rate coming in is Q. The flow rate coming out of pump one is Q1. The flow rate coming out of pump two is Q2. The pump head added by pump one is HP1, and the pump head added by pump two is HP2. Let's go ahead and also draw out the pump curves for these two different pumps. So I'm just going to draw, two arbitrary pump curves here. So this is our discharge on the x-axis, our pump head on the y-axis. Let's say the pump curve for pump one looks like this. And let's say the pump curve for pump two looks like this. So this is P2. This is P1. So you might have pumps with different pump curves that are being added together in series. So let's talk about how we can construct a equivalent pump curve that acts like these two pumps in series. So for a set of N as in November pumps in series, let's say we have the flow rate through one of these pumps. So if we have pumps in series and we have pumps P1 and P2, how are Q1 and Q2 related? What is the flow rate? How are the flow rate coming out of pump one and the flow rate coming out of pump two? How are they related? Let's assume the system is at steady state. Yes, they'll be equal. So for pumps in series, the flow rate through every single pump has to be the same. So I'll say that QI is equal to QJ for all I and J. So in other words, the flow rate through all the pumps is the same. All right, for the total head added by the pumps in series, it's simply equal to the sum of the individual heads added by each pump. So I'll say HP total is equal to the sum from I equals 1 through N as in November of HPI. So the total head added by the pumps is equal to the sum of the individual pump heads. So looking back at our set of pump curves here, let's say we want to draw the equivalent pump curve for these two pumps operating in series. How would we add these two pump curves together to get our new pump curve representing our two pumps acting in series based on these two rules here? Yes?
the vertical distance between P1 and P2, just like kind of.
Yeah, that's exactly right. So you stack the two pump curves on top of each other vertically. So you add together P1 and P2 vertically over their shared domain. So they're only defined over their shared range of discharges, but within that shared range of discharges, you can add the pump heads together. So let's say we have, a series of points here. And let's say this distance here is A. This distance here is B. You just add these distances together here. So we add A. Here we add B here. And the pump curve for the two pumps operating in series will look something like this. And remember that because the flow rate going through each pump is the same, it's only defined over their shared range of discharges. But this is the easier of the two cases. You just add the two pump curves together. Okay, sounds like you are pretty comfortable with that. So this is the pump curve for the pumps operating in series. Let's talk about pumps in parallel because it's a bit more challenging. Okay, so let's say we have two pumps in parallel. Call them P1 and P2. So there is some flow rate coming into this set of parallel branches Q, some flow rate Q exiting this parallel set of branches. Pump P1 is going to impart some pump head HP1. Pump P2 is going to impart some head HP2. There'll be a flow going through the second branch of Q2 and a flow going through the first branch of Q1. And let's say, just like before, that we have, pump curves for each one of these pumps. They're not necessarily the same. This is the discharge on the x-axis, the pump head on the y-axis. Let's say pump 1 has a pump curve like this. Pump 2 has a pump curve like this. So this is P2. This here is P1. And let's say for N is in November, pumps in parallel. First, let's look at the total flow rate going through this system of pumps. You can see from continuity that the total flow rate going through this system has to equal the sum of the discharges going through each branch, right? You have some flow rate Q going in that splits into some set of flow rates Q1, Q2, all the way through Qn is in November. When they converge back at the downstream side, that total flow rate in will be the sum of the flows through those branches. So the total flow rate is equal to the sum of all of the individual flow rates through each branch, which I'll call Qi, from I equals 1 through N is in November. So that makes sense. Okay, what about the total head? So how are the heads of the pumps related? So think back to circuits. What was the voltage across each branch in a parallel circuit? How are those voltages related? So that would be for the resistances. So it turns out that the head across each branch, the head imparted by the pump is the same. So we have that HI is equal to HJ for all I and J. So this might seem kind of strange at first, and you might wonder why this is happening. Let's take a look at applying an energy balance. We're going to go from, let's call this point A, the upstream end, to point B at the downstream end. I'm just going to draw this over again. So let's say we have our parallel pumps. And this is maybe relevant to some of the homework problems you're working on. So we have some discharge coming through, some discharge coming out. Pump 1 is applying some pump head HP1. Pump 2 is applying some pump head HP2. So we can apply an energy balance along any path. So first, let's select this upper path here. And we're going to apply an energy balance from point A at the upstream end to point B on the downstream end. So let's write out our full energy balance. We have ZA plus PA over gamma plus UA squared over 2G plus what else? HP1, so the head imparted by pump 1. This is equal to ZB plus PB over gamma plus UB squared over 2G plus the head losses from, I'll call it HL from A to B1 for the head losses over this upper path. So we can condense this. Let's just call this whole thing here H1, or sorry, HA. And let's call this whole expression here HB. So we have that HA plus HP1 is equal to HB plus the head loss from A to B over path 1. Okay, I'm kind of running out of space. Let me move this up here. So we can apply this same logic over the second path. So we're going to go from A to B over the second path here. We will have, so let me just label these. This is over path 1. This here is over path 2. So we'll have ZA plus PA over gamma plus UA squared over 2G plus what? Plus what? HP2 is equal to ZB plus PB over gamma plus UB squared over 2G plus the head loss from A to B over path 2. So this becomes HA plus HP2 is equal to HB plus the head loss from A to B over path 2. So let's assume that the head losses over these two paths are going to be basically the same. Let's say it's a short segment of pipe. So you're not going to get very many frictional losses over this length of pipe. So we're going to assume head loss from A to B over path 1 is equal to the head loss from A to B over path 2. So we will end up with HA plus HP1 is equal to HB plus, I'll just call it the head loss. We have HA plus HP2 is equal to HB plus the head loss. So what does this imply about HP1 and HP2? They have to be the same. So for pumps acting in parallel, if the head losses over each branch are assumed to be roughly equal, then the pump head applied by each pump will be the same. Yes. Can you repeat that? So the diameter would factor into this term UA and UB, right? So those UA and UB, these refer to these two pipe segments here that are outside of the two parallel branches. So that would end up in these terms HA and HB, but it wouldn't affect these two terms here. Now, it is possible that you might have different head losses over the different branches. I might give you a question like that. Just remember to apply the energy balance to figure out what's happening. So in this case, we can apply the energy balance and see that, if the head loss on one branch is different, how are the two pumps heads going to be affected by that? Yes.
But like the head has to be the same. That's.
Yeah, so you're basically the total head added and subtracted over each branch has to be the same because you're going from some point A to some point B, and there's a known difference in the head between those 2 points. So basically, yeah, the head gained or lost over a path, it's path independent. So let's go back to our drawing here. So we have that the total flow rate through this entire system is equal to the sum of the individual flow rates, and the head added by each pump is the same. So how can we add together these two pump curves to produce an equivalent pump curve for these pumps acting in parallel? Thinking analogously to how we did this for the pumps in series. Any ideas? So they have to be operating over the same range of heads. So they're going to be restricted to this shared range. And the flow rate is going to be equal to the sum of the flow rates through each individual pump. So how do we add together these two individual pump curves here? Yeah, we add them together horizontally. So it's analogous to what we did before. Let's say we just define a couple of points on here. And let's say we have some distance from the x-axis A, B. We add these distances horizontally. And we get our new pump curve for the pumps acting in parallel. That will look something like this. And it has to be over their shared range. So I'm going to remove this little part here. So this is P parallel. This is our pump curve for the two pumps acting in parallel. And yeah, if you remember back to circuits, it's analogous to how current and voltage behaved in circuits. with voltage being analogous to the head, current being analogous to the flow rate. So let's do a quick example. I'm going to walk you through how we can add together pumps in series and in parallel. So on Canvas, under Pages, there should be another Excel book called Pump Curve Combinations. Should look something like this. So go ahead and download that Excel book. And let me open it up here. Okay, so for the first sheet in our Excel workbook, we have two pumps that we're going to add in series. So we have our two pump curves here. We have a range of discharges that are shared between the two pump curves. We have our second column is the pump heads for that pump curve for pump one. Column C is the heads for pump two for our pump curve. So if we want the total head for the pumps acting in series, what do? B plus C, very good. So this is B plus C. And we can extend this down. And that gives us our new pump curve for the pumps acting in series. So that one is nice and easy. All right, now for the more challenging one. If you go to the next sheet titled Parallel, we have two pumps that are operating in parallel. So the first three columns describe our two original pump curves. So the discharge is given by column A. The heads for pump one are given by column B. The heads for pump two are given by column C. And this discharge in column A refers to the discharge for those pumps acting individually. Okay, so what we need to do here is we need to add together these two pump curves over their shared range. Range being the y-axis, the points where they're defined over the y-axis. So for instance, at a head of 300, we need to add together the x-coordinate for the blue curve with the x-coordinate for the orange curve. We need to do that for every point that we have defined here. So how can we do that?
Function in terms of X, you solve it.
You're on the right track. So yeah, we need to find for this set of heads here for pump curve one, we need to find the discharges that pump two will be operating at for those heads. And I've kind of given you a hint here for how we can do that based on the way the elements that are on this chart here. How can we find the discharges for pump two for this set of heads here?
Value associated with the other curve.
So the idea is we have this orange curve here. We want to find its discharge values for the set of heads for pump curve one. So at 300, we want to find the value of the discharge value on this orange curve. For 250, we want to find the value on this orange curve and so on. So we can do that by using our lines of best fit. So that's the approach we're going to take. So the first thing we're going to do is we're going to define a function for our second pump curve. And then basically we're going to give it a known value of the pump head. So this is HP, the Y value represents the pump head, the X value represents the discharge. So we're going to give it a known value of the pump head that we want to compute the discharge for. And then we do what? What do we want to find if we give it a known head value? Q, yeah. So we find the roots of this polynomial. I'm going to do that using Excel goal seek. You could also use Desmos or a graphing calculator to do that individually for each one of these pump heads. But let's start with an initial guess of 35 cubic meters per second for each of these. And our objective is going to be equal to the value of the polynomial evaluated at our guess for Q minus the pump head that we're seeking the discharge for. So we're going to try to find the discharge that will give us a head of 300 for pump 2. So our polynomial for pump 2 is given by this expression here. So we're going to have negative 0.2124 times the discharge squared minus 0.1321 times the discharge, which is E2, plus 360.37. So that is our polynomial, and we're going to subtract the head that we're trying to make that polynomial evaluate to. So now if I go to goal seek, I'm going to set cell D2 to value of 0 by changing cell E2. And if I do that, I end up with a discharge of about 16.55 cubic meters per second. Now note that if this is confusing, we could also set it up such that this cell here is just the value of the polynomial. And we want to set this value to which cell? B2. Won't let me click for some reason. So let's say B2 by changing cell E2. Oh, it doesn't let me do that. Anyway, I'll put 300 here. So we can do it either way. Yes. So we are trying to find the discharges for pump 2 that correspond to the shared range of heads for pump 1 and pump 2. So in this case, pump 1 is defining our shared range because it has a smaller range of heads. So we're using the head values for pump 1. Good question. So let's go ahead and do this same process for each of these discharges here. So we are going to have our polynomial here. And we want this cell to evaluate to, we're going to set cell D3 to value. What is our value here going to be? What pump head are we trying to make this polynomial evaluate to? Sorry? B3, which is 295.5 by changing cell E3. Okay, and we get a discharge of about 17.17. So I'm going to go ahead and do this for each one here. So this one, we're going to set D4 to value 282 by changing cell E4. We're going to set this one to value 259.5. So I'm going to continue doing this for each. And you should end up with a series of discharges that look like this. Okay, and when you complete computing all the discharges, you should get values for the discharges that look like this. Then for the total flow moving through the entire parallel pump system, what two columns do we need to add together? Right, we need to add A and E. So this is the total flow moving through the two parallel pumps. And you should get a combined pump curve that looks like this. So note that all we've done here is that we've added together the discharges over the shared range of pump heads. So that's what this whole operation was doing. If the procedure was confusing, just go back to that central idea and figure out how you can add those two pump curves together horizontally. Okay, so I have office hours today at 3. I will see you then.